What I'm going to be talking to you today about is an introduction to the advances we've made in machine learning over the last decade or so, and what this means for the kinds of processors we might want to design in the future, and also how machine learning might be used to help with these sort of chip design process. And this is joint work with many, many people at Google, so this is not purely my work. So AI has been a dream of people from the earliest days of computing. How can we make computers intelligent? And over time, what we've realized as a community is the only way that seems effective at making computers intelligent is instead of instructing them about rules about the world, you instead want to give them algorithms that enable them to learn from observations of the world, to learn from data and observations in order to be able to generalize to new situations. This is sort of how we learn things. And over time, we've realized that the rule-based approach for AI is likely to not work very well. And machine learning is going to be the way in which we make systems intelligent. And neural networks have been around for quite some time. They're a particular way of machine learning, a particular kind of model for machine learning. They're loosely based on how real brains behave. They're not exactly a brain simulation, but they are based on some neuroscience insights. And there was an initial wave of excitement about neural nets in the sort of 80s and 90s. In fact, as an undergraduate, I was actually very excited about them. I learned about them in a class, and I decided to do a senior thesis on how do we do parallel training of neural networks. Because I felt like if we could just get more compute power, 64 times as much compute power using a bunch of processors, we could actually do great things. And turned out I was wrong. We needed about 1 million times as much compute power, not 64 times. But what we've seen, starting in about 2009, we started to have enough compute power to make these systems actually do remarkable things that we don't know how to do in any other way. So the 2010s, I don't quite know how to refer to that decade, 2010s, I guess, was a decade of pretty remarkable progress in machine learning. I'm going to start the first part of the talk by outlining some of the progress in a few different important areas, and then we'll get into the rest of the talk. So what changed, really? A lot of what we're doing now is the same general algorithms that we knew about 30, 40 years ago. Backpropagation, gradient descent for training neural networks, plus, obviously, a bunch of new tricks that have been developed in the last decade. And we also now have more computational power. So it's possible to train models, to learn from observations, many more observations, use larger models with more parameters, more computation, and to use bigger models and deeper models, which I'll get into in a minute. Oh, what happened? So neural networks you can think of as learning complicated functions from data. Now, this isn't like y equals x squared. This is like, give me the pixels of an image, and I will tell you what's in it. Right? So that's a pretty complicated function. And deep learning is sort of a new name for the use of neural networks with many layers. They're deep because you have, instead of 2 or 3 layers like you had in the 80s or 90s, you might have 100 layers or 150 layers of these. And they're these powerful classes of machine learning models. Because they can build, because they're deep, they learn representations at each layer that build on the representations below them. So you can put in very raw forms of data, things like the actual pixel values of images or audio waveforms of speech, and then interesting intermediate representations emerge from learning from lots of data. And therefore, each layer is kind of a collection of trainable mathematical functions, and they're compatible with many different variants of machine learning. So a simple cartoon diagram, just to get everyone on the same page. Let's say we have a problem. We want to learn if that's a cat or a dog image. Right? It's actually a little hard to tell. And so we take in the pixels of the image, and in the simplest paradigm, that's called supervised machine learning, we have got a bunch of images where we've labeled them as whether that's a cat or a dog. And so we feed that in, let the model sort of propagate through the layers in a forward direction, or an upward direction in this diagram, and make a prediction. Is that a cat or a dog? And if the system gets the prediction right, great. If not, there are ways using backpropagation, essentially the chain rule and calculus, to make little adjustments to all of the parameters in the model in order to make it more likely that the next time you see an image like that image, or one with similar characteristics, you're more likely to make the correct prediction than the wrong one. And so that's the training process. You sort of iterate over the data, see what you predicted, if you get it right or wrong. If you get it wrong, you make little adjustments throughout the model. If you want intuitions about this, you can actually play with little teeny neural networks in your browser. It's actually a pretty fun little demo. If you haven't tried it, try playground.tensorflow.org. You can play with like 4 neurons and 2 neurons in 2 layers, and it will show you how sort of the training dynamics work. OK, so let's look at a few different areas of progress. So speech recognition, before people started really using neural networks at a large scale for this, the error rate for voice queries at Google was about 16%. And in 2012, we actually started using a neural network for the first part of the speech recognition system, the sort of the phoneme model, where you have you want to go from audio waveform of 50 milliseconds or so in length to a sound, a part of a word, like b or f or ts. And with using neural networks instead of the earlier, simpler machine learning approach for that, we were able to get a pretty significant reduction in the word error rate using a neural net for that kind of prediction. Then in 2017, we were able to use a neural net for the entire system. So going from raw audio waveforms to the actual words simply as a complete learned system. And that's actually made voice recognition on voice queries. I'm sure you've all been speaking to your phone more in the last few years than you were 5 or 6 years before that, because it's working much better than it was. And that really gets you over a usability threshold when the error rate drops significantly. And that error rate, 5.4%, was actually using a fairly large model that actually runs in a data center. In recent years, we've been working a lot on getting a lot of these machine learning models to be miniaturized and able to run on device so that they can actually run on your phone. And we're actually now able to get quite low error rates with a fairly compact model that can run on a phone. And this is pretty important because it gives better interactivity. It works in airplane mode, all those kinds of things. Computer vision is another area that's progressed a lot. And one of the real drivers of this has been this ImageNet challenge that was put together by Fei-Fei Li and others at Stanford University. And basically, it's a fairly challenging computer vision task where you're given a bunch of images, like the ones you see here. And the true labels are the ones you should see there. There's 1,000 categories of true labels. There's even a bigger one with 15,000 categories. And the goal is to train a model that can make a prediction, given the pixels of the image, what the true category is. And so models tend to make probabilistic distributions over the 1,000 categories. And the goal is to get as many correct in your top 5 predictions as possible. Obviously, the top 1 prediction is also important, but that's scored on the top 5 predictions. So let's look at the progress in ImageNet over the last years. So the contest started in 2010, and 2010, 2011, the error rate was around 26%, 27%. Didn't progress much from 2010 to 2011. And then in 2012, Alex Kruszewski, Ilya Sutskever, and Jeffrey Hinton decided to use a neural network with a bunch of interesting new tricks, including a technique called dropout and some other things, to basically create a system affectionately known as AlexNet, after Alex Kruszewski, that had a huge drop in the error rate in computer vision for the winning this challenge. And they were the only entrant that year that used a neural net. So in the next year, nearly all the entrants decided a deep learning approach was going to be a good one. And actually, that year was won by my former intern, Matt Zieler, and his advisor, Rob Fergus. And further reduction in the error rate. 2014, dropped again with a system called Inception, developed at Google. The next year, ResNet, developed by Kai-Ming He and others at Facebook. Significant reduction in error rate. And that's progressed and continued there. So that's pretty good progress in the last 6, 7 years. And one interesting thing that we know is human error rate is not 0% on this. It's about actually 5%. And we know this from a great blog post that Andrei Karpathy who was a grad student at Stanford at the time he wrote this post, did, where he sort of decided to subject himself to the proper machine learning training regimen, where he would sit down with a bunch of training images, kind of study them very carefully and try to predict, is that a St. Bernard or a prime minister or whatever. And then he would set those aside and he would do the proper machine learning test regimen, where now he would subject himself to new images he'd never seen before and try to predict the 1,000 categories. And he got about 5% error. He also had a colleague that he tried to this was after 120 hours of training that he did. He had a colleague that he tried to convince to do this experiment as well. They did about 15 hours of training and they got 12% error. It's actually pretty hard. There's like 40 breeds of dogs you have to be able to distinguish among the 1,000 categories. So we've gone from, basically computers not being able to see very well to computers being able to see, right? This is pretty big. If you think back to when animals evolved eyes, that was probably a time of great change, and we're in the same change for computing. Oh, what happened? Yes, please. I may have pushed the wrong button. If we can get back to where I was, that would be great. Sorry. I have not mastered clicking. And we've seen a similar story in natural language processing and machine translation. I'm not going to go through all the details here, but we've gone from basically a model where you can try to take an input sequence and predict an output sequence. This has all kinds of interesting applications for machine translation, where you take in an input sequence in one language, like hello, how are you today, and try to predict the output sequence in another language, various other kinds of things. And that was used to make significant improvements in accuracy in machine translation. And then a couple of words you might hear in the ethos. The transformer model was developed in 2017. The BERT model builds on transformers, was developed in 2018. Those are sort of important new advances in natural language processing. Okay. And one other area that I'd like to touch on briefly is reinforcement learning. So reinforcement learning is this idea where you have an agent, a computer model that's making predictions of actions that it wants to take in the world. And it has an environment. And the agent has some sort of goal, usually specified by a numerical reward function. And it makes observations about the environment. And given the current state of the environment and its goals, it tries to predict what action is going to be effective. And it makes actions in that setting. And then that interacts with the environment, and the state of the environment updates, and this loop continues. And this has been very successful in mastering a whole bunch of games. So in '95, there was some early work done on using reinforcement learning to master the game of backgammon to superhuman level. More recently, there's been work on using it to play Atari, very old Atari games, Atari 2600, if you remember back that far. From the raw pixel inputs of the Atari game. It's more recently been used to master the game of Go by my colleagues at DeepMind. And it's also been successfully applied to some games where you have only partial information available. So more advanced sort of strategy games like StarCraft or Dota 2 have shown remarkable success using reinforcement learning approaches. And the other thing that's been happening in the last sort of 6 to 10 years is that open source frameworks that make it easy to express machine learning algorithms and can map machine learning computations efficiently onto hardware that we use for these kinds of computations have actually made it very easy for people to express new and interesting ideas. This is a graph of several different open source packages. Scikit-learn, which is an older machine learning package, not necessarily targeting deep learning, and then 3 newer ones, TensorFlow in yellow, PyTorch in pink, and JAX in red, that have really focused on machine learning and in particular deep learning for making it easy to express those kinds of ideas. And this is a graph of GitHub stars, which is one measure of sort of use of those packages, or interest in them at least. And the other thing that's been happening is more and more people across many different domains, both in the pure machine learning algorithm basic research area, but also in a lot of different areas of applying machine learning to different fields of science or other areas of computer science, have really been sort of investigating how machine learning can be used in a variety of situations. And this is a graph showing essentially the exponential growth. The red line there is the Moore's law growth rate of 50% per year that we got so used to thanks to all of your great work in the last 50 years of remarkable progress in computational power. That's now kind of slowed down, at least for general purpose CPUs, but we've actually been exceeding that rate of growth for machine learning research output posted on arXiv. So this is a graph of the number of papers posted per year in the machine learning sort of tagged categories in arXiv. And you see it's actually growing significantly faster than 50% per year. So there's just a flood of activity happening in this space. And it's pretty exciting. And lots of people are doing interesting work in this space. And that's led to lots of amazing real-world applications. I'm not going to delve on these deeply, but really amazing work on medical imaging and other kinds of medical tasks. Now that computer vision works, medical imaging is one of the main application, a really interesting application area. Robotics, computer vision working is a significant advance for robotics. If you want to have robots operate in the messy world, it's really helpful if they can see. Self-driving vehicles are the same way. They need to sort of take in lots of raw data about the world from LiDAR and other camera sensors and other kinds of sensors, and build a high-level model of what's going on around the vehicle. Neuroscience, actually using machine learning to sort of analyze microscopy of scanned brain images and be able to reconstruct the connectivity of neurons is helping to lead to new insights in neuroscience. Agriculture, being able to have an app that sits on your phone and can tell you, is your cassava plant diseased, and if so, how are you going to treat it? And weather forecasting. These are just a sampling of the really interesting areas of uses of machine learning now that we can sort of see better and hear better. And there's a steady stream of using more computation to achieve better results. So this is a graph by some people at the OpenAI research group where they basically looked at increases in the use of amount of computation for, obviously not all machine learning results, but interesting advances in machine learning over the last, 6 or 7 years. And what you see, it's important to note that's a log base 10 scale on the y-axis, is that people have been using more computation to achieve more significant results in a bunch of different areas. And this is not just one area. This is including things like Plan Go or machine translation or computer vision work. So more compute seems to lead to better advances and better results. So if more computational power is needed, how can we get that computational power as effectively as possible, as with lower power requirements, faster processing? And deep learning in particular has some nice properties. So it's transforming how we think about computation. So two properties I'd like to draw attention to are, first, for all the stuff that I've shown you, reduced precision is OK. All the different composable units generally are fine with sort of 1 decimal digit of precision, not 5 or 6 like we've been gotten used to with IEEE 32-bit floating point. Certainly don't need double precision. And the other property is that they're all composed of different rearrangements of a handful of specific operations. Things like matrix multiplies, vector dot products, essentially dense linear algebra at reduced precision. If you can build computational devices that are really good at reduced precision linear algebra, that's going to be a great platform for doing deep learning. It's not going to be good for sort of twisty C++ code that we've gotten used to writing for CPUs, but for deep learning applications, this is really what you want to target. And so we've been thinking about sort of custom processing for machine learning for quite a while now. We actually started this project maybe in 2013 when we first started to realize that in particular inference, when you have a trained model and now you want to apply it, was going to be a big problem. So if you look at the speech recognition example, when we first rolled out a neural net for use in the voice search query system, we were kind of worried about the amount of computation that would consume if voice recognition started to work more effectively and people started to talk to their phone a lot more. And so inference was the first problem we tackled, where you already have a trained model and you just want to apply it to a new image or a new audio utterance. And so this is TPU version 1, tensor processing unit, that we developed and has been deployed for about 5 years in our data centers. It's used on every search query. It's used for machine translation, for speech recognition. It was actually used for the AlphaGo match. This is actually the rack of machines that we use for the AlphaGo match, so we pasted a little Go board on the side. And there's an ISSCC paper from 2017 that has details about that. So we tackled inference first because it's a bit of an easier problem, right? If you need most models at that time were fitting on a single chip. And so if you need more capacity, you just get more chips and you sort of have data parallelism across those, independent operation. They don't need to communicate really. And so you can just have an inference accelerator that works with even lower precision. Turns out for inference, you need even less precision than for training. And it's also really important to think about inference not just in data centers, but in low power environments. So we've been working on what we call edge TPUs, which are these very low power sort of accelerators for machine learning inference that actually work on low power environments like mobile phones or low power cameras, that kind of thing. So inference is all fine and good. And that was the first thing we tackled because it's a bit of a simpler system, simpler setup. What about training? And so let's get back to the precision aspect. So one of the things that's really important is being able to do lots and lots of multiplies per second in the system, particularly matrix multiplies. And if you think about precision, an IEEE 32-bit representation has 23 bits of mantissa, so you can build a sort of the mantissa portion of it out of a bunch of full adders. So you need one more bit than you have mantissa bits squared to deal with carries. And so an IEEE 32-bit floating point multiplier needs 576 full adders for the mantissa portion of it. An IEEE has actually defined a 16-bit format, which essentially reduces the number of exponent bits and also the number of mantissa bits from the IEEE 32-bit format. Now, it turns out that for machine learning applications, at least, it's actually much more helpful to keep the number of exponent bits the same as the 32-bit format, and even further reduce the number of mantissa bits, because we don't actually need that much precision. And what we care about is dynamic range. In fact, I'd rather lose all the mantissa bits before any of the exponent bits. And so we've come up with a format called bfloat16 that is essentially the IEEE 32-bit format with 16 less mantissa bits. So pretty simple format to define. And it turns out you can actually build multiplier circuits for this with significantly fewer adder circuits, which is good. Compared to the 32-bit, it's almost 8, 9x less full adders that are needed. OK, so then we've been thinking about systems for essentially training and inference. This is the second generation system that we came out with 2 or 3 years ago. 2 years ago, I guess, TPU v2. And this is a device with 4 chips on it. If we zoom inside one of these chips, it's essentially a pretty simple design, right? It's got essentially two cores, each with a giant matrix multiply unit, and scalar and vector units for things that are not matrix multiplies. But you really hope most things that you're doing are matrix multiplies. And then it has high-speed memory. HBM stacks, 16 gigs per chip. And then, TPU v3 is essentially a relatively modest design improvement over that. We've added liquid cooling. It's always exciting when you have water next to your chips. We've only had a few leaks. And then these systems are designed to be connected together into larger scale systems. So this is what we call a TPU v3 pod, which is 1,024 chips, essentially connected in a 32 by 32 toroidal mesh. Collectively, those chips have more than 100 petaflops, about 106, 107 petaflops of compute. And the reason that's important is it enables us to scale to larger problems and also to get more rapid feedback on machine learning experiments we want to do. So for example, training a ResNet 50 ImageNet classification model from scratch can be done in less than 2 minutes on one of these pods. And that's basically processing the entire ImageNet training data set roughly once a second. And training a language model can be done relatively quickly as well. But really, large-scale computation applied to these problems is going to be the way that we make faster progress, because it enables you to do different kinds of research if the experiment you want to do takes a few minutes rather than a day or a week or a month. OK, so we've been doing a bit of work on machine learning for device placement. So one of the trends is that models are getting bigger so that the entire model doesn't necessarily fit on a single chip. And so if you have essentially large models, then model parallelism, dividing the model up across multiple chips, is important. And getting good performance given a bunch of compute devices is non-trivial and non-obvious how to do that effectively. So these are sort of just diagrams to show you that the models are getting fairly complicated, and it's not always obvious where to put those different pieces of computation if you have multiple devices. And so device placement as an RL problem, as a reinforcement learning problem, is an interesting thing to look at. So you have some model of computation you want to do, and then you have a set of available devices, and you want to map different pieces of the computation onto those devices. And it turns out you can use an RL model where the actions that the model takes, that the placement model takes, are placing part of the real machine learning model you care about onto different devices. And when you've placed them all, you can then evaluate the runtime, get feedback on how well that worked, and repeat and update the model so that it gets better and better at placing this computation. And so it does kind of non-intuitive things. So this is a model of computation that we wanted to place. And the different colors, there are 4 different GPU cards that we had in a single machine. And the white color is the CPU. So it turns out like it actually figured out how to creatively use all the different GPU devices and also intermix some CPU usage, because the CPU would otherwise be idle, in ways that a human expert would not necessarily even have thought of. And we've been sort of doing further work on this so that we can scale to larger models where you have, say, 80,000 nodes in the computation graph. Can we train a placement model instead of just on the particular model we care about, train it on a bunch of different neural network models, and then learn to generalize to a new model we've never seen before to do a good placement of that relatively quickly. The general reason I'm bringing this work up is then we started to think about using this, instead of using it to place software computations onto different computational devices, we started to think about it for, could we use this to do placement and routing in ASIC chip design? Because the problems, if you squint at them, sort of look similar. And so reinforcement learning works really well for hard problems with clear rewards, like chess or Go. And essentially, we started to ask ourselves, can we get a reinforcement learning agent to successfully play the game of ASIC chip layout? Right? Now, there are some challenges here. First, the state space is much bigger even than Go. And in particular, the problem size is very large. You have millions or billions of items. You actually have multiple objectives you care about, not a single objective like in Go, where you want to win and not lose. Here, you care about area and timing, congestion, design rules, and so on. And the true reward function is actually very expensive to evaluate. It's many hours to run EDA tools on a particular evaluation. And so we have an architecture model that I'm not going to go into a lot of detail, but essentially it tries to take a bunch of things that make up a chip design and then try to place them on the wafer, and actually, or the chip design, and actually learn to do that, taking actions to place this component, then this component, then this component. And so here are some results from a low-power machine learning accelerator chip. And some areas are intentionally blurred. But essentially, we've had a team of human experts place this IP block. And we have a couple of proxy reward functions that are very cheap for us to evaluate. In particular, we can evaluate them in a few seconds instead of hours, which is really important for reinforcement learning because you want to be able to iterate many times. And then we have a machine learning based placement system. And what you can see is the machine learning placement system has sort of spread out the kind of the logic a bit more rather than having it in quite such a rectangular area. And that's enabled it to get improvements in both congestion and wire length on this metric. And we've gotten comparable or superhuman results on all the different IP blocks that we've tried so far. So here are 3 different blocks with a few different metrics about each block, the worst negative slack, the total negative slack, and then some measurements of area, chip area. And you can see generally the machine learning placement system does a little bit better or significantly better than the human effort. And here's the results on a TPU design block. The white blurred areas are macros. The green blurred areas are standard cell clusters. And the machine learning placer essentially finds sort of a smoother and rounder macro placements to reduce the wire length. The time taken here was about 24 hours for the machine learning system, or 6 to 8 person weeks for the sort of expert humans doing this. So one question is, can we train a general agent that is quickly effective at placing a new design as never seen before? And so what we see is that here's a graph showing several different blocks. 1 through 4 are TPU blocks, and then we also have an Ariane RISC-V CPU block, which is an open source CPU design. And then we have the wire length cost, with lower being better here. So we have a commercial tool in green. We have a zero shot, so a model that we've trained on a bunch of other unrelated designs and then applied to a completely new design it's never seen before. And the first thing it does is shown in the lightest blue. And then if you fine tune that model, so give it 2 hours of training, additional training on the particular block that you care about, it does significantly better, a bit better or significantly better depending on the design. And then if you give it 12 hours then you get essentially the darkest blue. And if you train the system from scratch without giving any pre-training on other blocks and just let it go from initial blocks to placing this particular design, that's the yellow bar in 24 hours. So you can see that experience on other designs actually improves the results significantly. And so essentially in 12 hours, you can get the darkest blue bar. And this is a graph showing the wire length cost, where you see if you train from scratch, it actually takes the system a little while before it sort of makes some breakthrough insight and is able to significantly drop the wire length cost, whereas the pre-trained policy has some general intuitions about chip design from seeing other designs, and it's able to get to that level very quickly. And I have an animation of this. So this is the Ariane RISC-V block that we were talking about. Each of the cells with a square is a macro, and the sort of empty areas are the standard cell logic. And you can see the pre-trained policy already knows it's a good idea to put all the logic in one sort of contiguous area, whereas the policy from scratch iterates a lot of times before it sort of redevelops this intuition, or initially develops this intuition that putting all the logic together is a good idea. And if you wait to the end, you can see they both kind of develop this notion that putting that logic there is a good idea. Okay, so there's potential benefits of machine learning-based placement and routing. I think this can allow ASIC designers to quickly generate many alternatives with different trade-offs in terms of area and timing, quickly redo the layout if something upstream the design changes. Even if there were major changes, in 12 hours you can get a pretty good, quite good placement. And it might significantly reduce the time and effort needed to develop new ASICs. I think there's many other applications of machine learning to ASIC design in this community, and others are exploring that quite extensively. ASIC design verification, in particular, high-level synthesis, I think is a really important thing. If we now can automate a lot of the placement, maybe we can do a much better job of making high-level synthesis to an actual chip work more effectively than it has in the past. Okay, I'm going to close with what might future machine learning models look like. So today, we're mostly training machine learning models for a particular task. And then for a new task, we sort of train a different model. And we don't generally get a lot of transfer learning from one task to another. Occasionally, we do this where we transfer learn on one task and fine-tune on a related task, as I showed you in this example. But we're not doing this at a large scale. So I think in the future, we're going to want single models that do many, many different things so that we can leverage expertise and experience on these things. And maybe we want a single model that does thousands or millions of tasks, with new tasks being able to be added all the time. These systems would be large, running on hundreds or thousands of machine learning compute devices, but they'll be sparsely activated so that any given example or task might only touch tens or hundreds of the devices, not all of them. So a few percent of the total compute. And the model structure mapped onto these devices might change dynamically through things like meta-learning algorithms. So I think that's kind of a glimpse at where I think one interesting direction is going to go, and what implications that might have for hardware designs is going to be interesting. So in conclusion, ML is changing much of how we think about computing. It's really enabled us to now see and hear and understand language better than we were able to before. And it's really bringing about new kinds of computing devices for machine learning acceleration. Application to chip design, I think, is an interesting one. As part of the keynote, I was asked to write up a companion paper. I want to highlight it here because it was a lot of fun to write, and I want you to all experience it. And thank you. There's more info about our work at that URL. Thank you very much.